So, the next topic in this solid state chapter important is after this arrangement of atoms. As we have seen in the primitive unit cell, the occupied volume is only 54%, and in body centered cubic it is only 68%, and the maximum packing fraction is that in FCC and HCP, that is about 74%. So, in spite of maximum efficiency, the efficiency here, maximum efficiency means it is limited only to 74%. So, still there is a vacancy of 36%. 36% is the vacancy in the HCP and FCC, whereas in the BCC it is about the voids is the important thing that what we have to discuss. As we have seen in HCP and CCP, in spite of maximum efficiency, because they are the ones what we are calling them as a packing with maximum efficiency, close packing. So, in spite of we are calling it as close packing with maximum efficiency, it is limited only to 74%. So, here the maximum is only 74. So, still we are left with 26% of empty space. 26% is the minimum empty space that should be left, that is always left in the packing, minimum void space. And in the case of BCC, it is 68% is the packing fraction, so 32% is left unoccupied. And in the primitive, already we have seen it is 54% is occupied, so another 46% is left unoccupied. This unoccupied spaces, these empty spaces in any type of this crystal lattice is what we call it as void. So, void is void space. Void space is, the void space is nothing but the empty space in the packing of crystal lattice. In the HCP and CCP, the void space is about 26% in spite of maximum efficiency. So, the void space is the empty space that is formed. Now, this empty space again has a particular geometry, and what is that particular geometry, and in that space what other atoms or ions that can be accommodated, because this is basically calculation of this void space and void geometry is very important with respect to ionic crystals and even covalent crystals also. For example, if you take the case of sodium chloride crystal, what we will say is that in the types of crystals in the ionic solids, we discuss them in detail. The chloride ions will form the whole lattice, chloride ions will form the whole lattice, FCC lattice, and sodium ions we say that they will occupy all octahedral voids. So, what is an octahedral void and why sodium ions only will occupy that? Why not the chloride ion occupy the octahedral void? What is the reason and what is the geometry? What is the condition? That all is what, if you look at it, the void spaces are mainly two geometries. They are mainly of two types. What are those two types? The main two types that are, one is tetrahedral void and second one is octahedral void. What is a tetrahedral void and what is an octahedral void? Tetrahedral void is, of course, the geometry of the void is tetrahedral. If the geometry of the void is octahedral, then we call it as octahedral void. Does it mean that only these are the two voids that are formed? No other void is going to be formed? The answer is that the type of void formed depends on the type of layer arrangement. Suppose if it is primitive unit cell. If it is a primitive unit cell, then as 4 atoms on one layer, 4 atoms on another layer, if they are like this, in the middle that what you will have is some empty space that is a cubical void. And in the BCC, that if you look at it again, at the center you have, and in between you still left with certain void space, that is of it. So this is, first if you look at it, two dimensional. This is one type of arrangement. This is another type of arrangement. Or the two, if you compare, here this is a square void, this is square, and here you can keep one sphere, and this is a trigonal void, and here you can keep one sphere. Both if you compare, as you can see very easily, in this arrangement void space is more, this being a square void, and here the void space is less. That is the reason, in fact, this is the arrangement in both HCP and CCP, and where the void space is less, packing efficiency is more, right. Then in the, this is a square void, then on top of this if you keep another 4, then what you will get is, if same A, if suppose this, if you consider it as layer A, and all A type arrangement if you continue, then what you will get is primitive, and here what you will get is cubical void. And instead if you keep, if these two are little, here of course A equal to 2R, but instead in the BCC, just if you pull these two little outward, that means the two spheres are not in contact, and then if you speak, then that means if you have it like this, then this is what AB, this will give you body centered type, and here again with an extended view you will get again a cubical void. But now coming over here, this is more important for us, this FCC and HCP cases you speak, this is the arrangement of atoms in layer 1, and then in layer 2 you have atoms like this. When you arrange the atoms like this, so here this is a tetrahedral void and this is octahedral void. This is a tetrahedral void and this is octahedral void, means this is tetrahedral void, because here it is, here if you keep a sphere over here, this sphere is in contact with 3 spheres like this and 1 sphere on the top. So this is a tetrahedral. Then on the other way, that if you have spheres like this tetrahedral void, now octahedral void, now I will draw it and I will show you how the octahedral void appears. So if we arrange the atoms like this, then this is on top of it, if you keep another sphere, then this empty space what is left is what we call a tetrahedral void, because here this is the atom, this is in contact with 1 sphere, first one, second one, third one, second, third, and 1 sphere, this broken line sphere that is on top, that I will show this is the 4th one. So this is what the tetrahedral void appears. So coordination number for tetrahedral void is 4. So what is a tetrahedral void? Tetrahedral void is nothing but the empty space that is formed from 4 mutually touching spheres arranged in a tetrahedral disposition. Empty space formed by set of 4 spheres that are arranged in a tetrahedral disposition is what we call tetrahedral void. So that empty space in between, if you keep one sphere, one small sphere that you can keep, what small, what should be the size of that small? that depends on the size of the atom, right. So, for this we have to go for a mathematical calculation to know what is the volume of that particular empty space. So, any ion or atom that can be fit in that particular empty space is only the one that is suitable over there, right. So, based on the other ion or atom that is going to occupy the size of that, the crystal structure is what we are going to define, or what is the ion or atom that forms first of all the basic structure. From that, what is the size of that? The size, the volume or the size of that particular void in relation to the size of the atom. That is what in the case of ionic crystals we refer it with the radius ratio, ratio of cation to ratio of anion, that in the ionic crystals we will discuss. So, that is nothing but actually what we have to define is what is the volume of this. So, only the atom or ion that fits over there, that particular size of ion or atom only, that what we have to take. Now, coming to octahedral void. Octahedral void is, so suppose if you keep one set of atom like this, so in the arrangement, now if you have 3 spheres like this, these 3 spheres if you consider, one sphere like this, 3 other spheres like this, then this empty space that is formed. So, 3 spheres like this, first in layer A, and this is layer B, then in between whatever the space that is left, this is layer A, this is layer B. Then 3 spheres like this and 3 spheres like this when you keep, total 6. In between if you keep one particular sphere, that particular sphere is actually the one that is placed at the octahedral disposition of 6 mutually touching spheres of 2 different layers. So, that is what the octahedral void. So, this is what we call octahedral void. So, this is the space. This is tetrahedral void. This is octahedral void. So, this octahedral void, now on top of this if you keep one sphere, then we will get our ABC type. So, ABC type, that is FCC. In FCC, we actually doing is, we are covering the octahedral void formed from the 2 successive layers A and B. Whereas in HCP what we are doing, we are covering the tetrahedral voids formed from 2 successive layers. So, this if you cover, this is if you are covering, what you are getting is ABC. I mean AB, that is HCP. If you are covering this, as we told, 1, 2, 3, these 3 spheres, this is what you will get, FCC type, right. So, overall for both HCP and FCC, the possible voids are, so therefore, for both FCC and HCP, only tetrahedral void and octahedral voids are formed. Now, the exact formation of this tetrahedral void and octahedral void more clearly with the help of slides, now we can see. Start this slide please. The types of voids, octahedral, tetrahedral, found in both FCC and HCP. First, octahedral void in FCC. Now, if you take a particular atom at the 2 corners, the white balls, and the red ball is edge center, that particular edge, if you look at it, red ball is at the edge center, 2 white balls at the 2 opposite corners of the same edge, then 1 white ball is at the face center and another white ball is at another face center, that is back face it is, right. Overall, now if you look at it, the red ball is in contact with 2 white balls of 2 opposite face centers, 2 white balls of that back faces and 2 white balls on the corners. So, it is each octahedral void located at the edge center is shared by 4 unit cells. Total contribution of edge center voids is for 1 by 4 into 12, because an atom at the edge center is already we told it is 1 by 4. and we will have 12 such edge centers. So 12 into 1 by 4 is equal to 3. So basically the position of an octahedral void in FCC is at the edge center and at the body center. This is the body center. So one we have seen earlier is the octahedral void formed at the edge center. Now here you see the red ball. Now the red ball is at the body center. Now the body centered red ball is in contact with all white spheres that are positioned at centers of 6 faces. That is a top face, bottom face, right, left, front, back. So this is the octahedral void formed at the body center. So octahedral voids are formed at edge center and body center. If you consider the edge center voids, then you will have 12 edge centers. Each of that octahedral void contributes 1/4, and so total octahedral void from the edge centers are 3 net contribution, and 1 is at the body center. So overall number of octahedral voids in FCC is equal to 4. 4 in the total number of octahedral voids in FCC unit cell are 4. That means number of octahedral voids is equal to rank of the unit cell. What is rank of the unit cell? We told rank of the unit cell is nothing but number of effective atoms. Number of effective atoms in FCC are 4. Number of octahedral voids in FCC are also 4. So number of octahedral voids is equal to rank of the unit cell. Tetrahedral voids in FCC. Now if you consider one atom at the corner, one atom at the face center of the top face, one atom at the back face, one atom at the side face, all 3 are at the centers. Now that if you consider, if you look at it, all the 3 axes and of course their positions. Now this red ball is along the body diagonal. From that 0, 0, 0 reference atom, if you consider white one, from the 0, 0, 0, this 0, a by 2, a by 2, a by 2, a by 2, 0, a by 2, 0, a by 2. These 3 spheres are face centers. Then the red ball is the one that is along the body diagonal. That is at a distance of a by 4, a by 4, a by 4. From the white ball at 0, 0, if you draw a diagonal to the opposite one along the body, then this red ball is present at along that body diagonal. So along that body, you have diagonal, you have one, and this is how the tetrahedrali they are placed, and that angle is, of course, you can measure it like this. Of course, this calculation is not that important for us. So overall, now if you look at it, this is again another tetrahedral void. Now as we told that a tetrahedral void is formed along the body diagonal at 1/4 distance from corner. So along each body diagonal you will have 2 such spheres, 2 red balls, right. So body diagonals we have total in number 4, and along each body diagonal we have 2. So number of tetrahedral voids is equal to 2 into number of body diagonals. Number of body diagonals are 4, that is 2 into 4, 8. So in total what you can say is that number of octahedral voids is equal to rank, and number of tetrahedral voids is equal to 2 into rank of the unit cell. Now this is voids in hexagonal. Now in this hexagonal, if you look at it, similar to FCC, this is what actually hexagonal void means. The space that is left at the junction of 3 yellow spheres and 3 blue spheres is what is an octahedral void. This is hexagonal face. Then these are the 3 spheres in between. So now from this, if you look at it, the number of octahedral voids, in FCC we told is equal to rank. Here also number of octahedral voids is equal to rank. This is what the octahedral void, that exactly that center one, that is octahedral void. And the tetrahedral void is again the same thing. and the number of tetrahedral voids is here again equal to 2 into rank. So, overall in HCP, number of octahedral voids is equal to rank, that is equal to 6, and number of tetrahedral voids is equal to 12. So, this totally gives us the number of octahedral voids, number of tetrahedral voids. Coordination number in tetrahedral voids is 4, coordination number in octahedral void is 6. Either in HCP or FCC, number of octahedral voids is equal to rank, that is number of effective atoms, and number of tetrahedral voids is equal to twice the rank. So, in FCC, octahedral voids are 4, tetrahedral voids are 8. In HCP, octahedral voids are 6, tetrahedral voids are 12. Then in the next, what we have to say is the size factors, radius ratio rules and ionic crystals is what we have to look into it.